Great seeing you here again. My name is Luc de Kuster, founder of the Kuster Academy, and in this video I'm going to look at how we can apply Pert and 3Point on an activity on the arrow diagram. We spoke about these diagrams, we looked at the arrow diagramming method, but what we are going to do now is what we call creating a Pert diagram. Now we still use the term Pert, related to the fact that originally everything came from the Pert estimate, that a plus 4m plus b divided by 6 and b minus a divided by 6 for the standard deviation. We can also use the results from the 3-point estimate, which is a little bit easier. Now let's have a look at this, but before we continue, don't forget to click on the subscribe button, click on the bell button, and every time we have a new video, YouTube will inform you about it. So let's have a look at what data we have available. Now, when we originally looked at the arrow diagramming method, we considered the duration of the activities as fixed. Now, the results of this were not so good, and people were looking for additional information. And from statistics, we know that whatever we measure, whatever we do, even when we do it 100% correctly, there is variation, the common cause variation. And that was added to those estimates. First, people used a beta distribution, a little bit more complex distribution, and later they also introduced a triangular distribution, typically used in the case that we are not sure about the probability distribution of the activities. Now we can use both. Today we have typically the triangular distribution because the calculation is a little bit easier. The 3-point estimate is optimistic plus pessimistic plus mode divided by 3. The standard deviation is still b minus a divided by 5 in this case. So we get a little bit higher average and a little bit higher standard deviation. The element what we get is that we find an estimate which has a 50% probability of being exceeded, or that the duration is less than that value. And we also have a standard deviation, and we know from the normal distribution that we can calculate the duration or the probability that in our case a duration will be less than a certain value. For example, we have a 84% probability that the duration will be less than the average or the mean plus 1 standard deviation. Now let's have a look at our schedule. You see the schedule here. This is the same schedule that we had before. We have 3 activities without predecessors, A, B, and C, so they all start from the node 0. We have an activity D with predecessor A. Then we have an activity E with predecessor B. We have an activity F with predecessor B and C, and that's why we have the dummy between the nodes 2 and 3 to create that precedence on the diagram. And G, we have the same thing here with the dummy. We have the predecessors D and B, so we need the dummy which connects nodes 2 and 4 and adds the precedence relationship to the graph. The first thing we're going to do is to add the information about the duration and the standard deviation. The first number is the duration for A 4.5, and there is a standard deviation of 1.5. For B, we find a duration of 2.3 with a standard deviation of 0.5, and for C, a duration of 1 with no standard deviation and standard deviation 0. Now you may wonder, where do these numbers come from? Well, in our case, they are obtained from the Pert or the 3-point estimates. We have those calculations. We know the optimistic, the pessimistic, and the expected value, the mode. Now, these are elements that we can consider here, and we can calculate that. We can use those formulas. We can have them obtained from a different estimation. For example, we have some probability distribution that leads us to these numbers, Monte Carlo or whatever statistical tool we may have. Typically, it was only used with the Pert and the 3-point formulas. Now we have A, B, and C. Let's have a look at D, which has a duration of 2.5 and a standard deviation of 0.8. E, a duration of 3.4 and 0.8. F a duration of 2.3 and 0.2, and G a duration of 5.3 and a standard deviation of 1.2. Now we can start with the calculations. We start with A. A starts at the event, or the event 0 takes place, the start of A, the tail event is 0. The head event 1 finishes at time 4.7, 0 plus 4.7 is 4.7. We do the same for B, so we go from 0 to 2.3, and from C, we go from 0 to 1. Now we have to continue, and we have to determine what is the start, the early start of the follow-up activity. So for D, we only have one activity arriving in the node 1, so we can say 4.7. The end time of A is also the end time of D. So we find 4.7. We add 2.5, so we find 7.2, which is the end time of activity D. We do the same for the other activities. We have the dummy. The dummy has a start time which is equal to the finish time of B. The duration of the dummy is 0, so the end time of the dummy is also 2.3. And we already see at activity 4, or at event 4, we have in fact 2 times that we have to consider, and we will have to continue with the highest time because both activities D and B have to be finished, or in this case D and the dummy. For E and the dummy, we also find the starting time of 2.3. There is only one input here. The dummy also has a starting point of 2.3, and of course an endpoint of 2.3 because there is no duration on the dummy. Now we continue with the activity F, so we take the highest value that enter the node 3, so it's 1 and 2.3, so F can only start when both activities are finished, so the starting time of F is 2.3. We do the same thing for the activity G. We have 2 entries, 7.2 and 2.3. We take the highest number, so the early start of G is 7.2. We calculate the endpoint for E, so we have 2.3 plus 3.4, which gives us 5.7. And for F, we do the same, we find 4.6. And the last activity G, the end time of G is 12.5, which leads to the project duration in this case. So the project duration is 12.5 periods. Now we found the periods, now we have to add the standard deviation. The duration is 12.5 periods, which is the sum of all the activities, the duration of the activities on the critical path. And we can do the same for all the other paths. And when we look at this, we will see that the path ADG is clearly the longest path through the network, and we know that this is the critical path per definition. Now we have to find the standard deviation of the critical path, and we have to look at the standard deviations of the activities, but we cannot add standard deviations. We know that from statistics, we can only add variances. So when we look at the standard deviation of the critical path, we have to say that this is equal to the square root of the variance of the critical path, and the variance of the critical path is obtained by adding the variances of the activities on the critical path. So the standard deviation to the square of A, the standard deviation to the square of D, and the standard deviation to the square of activity G, which gives us 1.5 to the square, plus 0.8 to the square, plus 1.2 to the square, and you can calculate this, that this is the square root of 4.33, which is equal to 0.08. Now, when we look at this, well, we can make an estimation what it gives us as an estimation. Now we know that there is a 50% probability that the project will finish in less or more than 12.5 periods. But when we add one standard deviation, so we can also say 12.5 plus 2.08 is 14.58. We can say that there is an 84% probability that the project will finish in a time less than 14.58 periods. And that's what we wanted to do with the activity on the arrow method, the application of the Pert method on this diagram. And the only thing that we change is that we add that uncertainty. We now have activities which have decimal values, but it doesn't change anything because the formulas are really adjusted for this. We're using the events, we're not using the ordinal numbers, and we can calculate these quite easily. So we find an expected duration or a duration with probability of 50% and a standard deviation. So we can apply this to make more, let's say, statistical approaches to the duration of the project. And we can say, when somebody asks us, what's the probability that the project will finish between so many and so many periods, we can say, okay, we have the average, we have the standard deviation, so we can calculate the probability. So that was it for this video. Thank you very much. Don't forget to click on the subscribe button, click on the bell button, and every time we have a new video, YouTube will inform you about it. Thank you very much, and I'm looking forward to seeing you in our next videos. Bye-bye.